Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1932 marks a pivotal moment in the history of physics, witnessing Carl Anderson's groundbreaking announcement of the positron's discovery. This essay undertakes a thorough examination of Anderson's seminal paper, dissecting its claims, evaluating its methodologies, and contextualizing its lasting impact on scientific understanding. We will delve into the specifics of his experimental setup, the logic of his deductions, and the strength of his evidence, providing a critical assessment of this landmark contribution to the field of particle physics. Section 1: Introduction and Initial Observations. Anderson's 1932 publication presents a compelling narrative of experimental investigation, born from the meticulous study of cosmic rays interacting with matter. He begins by acknowledging the theoretical predictions of Paul Dirac concerning the existence of antiparticles, specifically a positively charged electron. However, Anderson emphasizes that his work remains independent, focusing on empirical observation rather than direct validation of theoretical constructs. The initial claim presented is that photographic plates exposed to cosmic rays within a strong magnetic field revealed tracks exhibiting curvature inconsistent with known particles, namely, negative electrons and positive protons. These observations necessitated the proposition of a particle possessing a mass of an electron but bearing a positive charge. The significance of this initial observation cannot be overstated. It challenges established paradigms and paves the way for a new era in particle physics. Section 2: Experimental Setup and Cloud Chamber Technology. A critical component of Anderson's discovery lies in his refined use of the cloud chamber. His paper details the chamber's construction, emphasizing the meticulous design necessary to achieve clear and interpretable particle tracks. A lead plate bisects the chamber, providing a mechanism for measuring particle energy loss, and thereby estimating its mass. Anderson described the application of a strong magnetic field, generated by electromagnets, perpendicular to the chamber. This field, measured at 24,000 Gauss, allows for the precise determination of a particle's charge and momentum based on the curvature of its path. The claim here is that the cloud chamber, coupled with the powerful magnetic field and the lead plate, provides a robust system for differentiating particles based on charge, momentum, and energy loss. The precision of these measurements becomes crucial to supporting the existence of a particle distinct from protons and electrons. The photographic recordings of these tracks serve as primary data, demanding careful interpretation and validation. Section 3: Analysis of Key Cloud Chamber Images. Anderson's paper hinges on the presentation and interpretation of specific cloud chamber photographs. He focuses on one image in particular, describing a track exhibiting a curvature indicating the positive charge, while simultaneously demonstrating an ionization density consistent with an electron, not a proton. The track traverses the lead plate, exhibiting a reduction in momentum as it passes through. Anderson argues that the change in curvature, along with the ionization density, definitively rules out the possibility of a proton. Furthermore, he dismisses the possibility that the track could be due to an electron traveling in the opposite direction, since such a scenario would necessitate the electron originating from the lead plate with an improbably high energy, a conclusion deemed less probable given the experimental configuration. This detailed analysis of the key image serves as the cornerstone of Anderson's claim. The visual evidence, meticulously described and interpreted, seeks to eliminate alternative explanations and solidify the proposition of a new particle. Section 4: Differentiation from known particles and proposed identity. Having presented evidence for a positively charged particle with a mass comparable to that of an electron, Anderson dedicates a section to systematically excluding previously known particles. He reiterates that the observed ionization density is far too low for a proton and that the track's curvature is inconsistent with a positive proton's expected behavior within the magnetic field. He also addresses the possibility of the particle being a heavy positive ion but argues that the observed frequency of such events contradicts this hypothesis. Ultimately, Anderson concludes that the only plausible explanation is the existence of a previously unknown particle that he proposes to term the positron. The claim here is not merely the observation of an anomaly but the identification of a fundamentally new constituent of matter. This proposition required rigorous exclusion of existing explanations and a bold assertion of a previously unseen particle. Section 5 Measurement of positron energy and momentum. Anderson provides quantitative estimates for the energy and momentum of the observed positron, further solidifying his claims. By measuring the track's curvature before and after passing through the decay, calculates the energy loss incurred by the particle. He uses these measurements to estimate the particle's initial energy and momentum. These calculations, though subject to the limitations of cloud chamber technology, provide crucial evidence supporting the claim that the observed particle possesses properties consistent with Dirac's predicted positive electron. The numerical data, derived from visual analysis, offer a level of rigor to the qualitative observations. The precision of these measurements, within the context of the experimental setup, reinforce the validity of Anderson's interpretation. Section 6 Discussion of theoretical implications and Dirac's prediction. While Anderson initially emphasizes the empirical nature of his discovery, he acknowledges the profound theoretical implications of the positron's existence. He discusses Dirac's whole theory, which predicted the existence of positively charged electrons as holes in the sea of negative energy states. Anderson concedes that his experimental findings provide strong support for Dirac's theory, bolstering its credibility within the scientific community. However, he avoids explicitly claiming that his discovery is solely a confirmation of Dirac's prediction, maintaining a degree of scientific independence. The significance lies in demonstrating the convergence of theoretical prediction and experimental observation, strengthening both the theoretical framework and the validity of the experimental findings. Section 7 Addressing potential sources of error and uncertainty. Anderson briefly considers potential sources of error that could influence his results. He acknowledges the limitations of cloud chamber technology, admitting that the precision of measurements is constrained by factors such as chamber turbulence and distortion of the photographic images. He also discusses the difficulty in accurately determining the ionization density of the particle tracks. However, Anderson argues that even considering these potential sources of error, the overall conclusion regarding the existence of the positron remains robust. This acknowledgement of limitations demonstrates scientific integrity and highlights the awareness of potential biases. It shows that the overall claim is strengthened by the critical consideration of its own limitations. Section 8 Contemporary reception and validation by. Following Anderson's publication, other physicists quickly sought to replicate and validate his findings. Several independent experiments, using similar cloud chamber techniques, confirmed the existence of the positron. These validations, published in prominent scientific journals, solidified Anderson's claim within the scientific community. Of particular note is the work of Blackett and Occhialini, who independently observed positrons in cosmic ray showers. The rapid confirmation of Anderson's discovery highlights the impact and importance of his work, prompting a paradigm shift in the understanding of fundamental particles. The independent validation provides strong external evidence for the accuracy and robustness of his initial claims. Section 9. The Neddermeyer and Anderson cloud chamber experiment. Subsequent work relevant to claim. Building upon the initial discovery, Anderson, in collaboration with Seth Neddermeyer, further refined cloud chamber techniques and investigated the properties of cosmic rays. Their subsequent work focused on detailed analysis of energy loss and range relationships for various particles, including positrons. They observed that positrons, upon encountering atomic nuclei, could undergo a process of annihilation, transforming into photons. This observation provided further insight into the nature of antimatter and its interaction with matter. This elaboration of positron properties, obtained in subsequent experiments, enhanced and broadened the understanding of the initial discovery. It demonstrates a consistent line of inquiry that stems from the initial observations. Section 10. The implications of pair production. A key implication of Anderson's discovery and subsequent research was their understanding of pair production, the process by which a high-energy photon transforms into an electron-positron pair. This phenomenon, predicted by Directives theory, provides direct evidence for the conversion of energy into mass, as described by Einstein's famous equation, energy equals mass times the speed of light squared. The observation of pair production not only validated Directives theory, but also deepened understanding of the fundamental relationship between energy and matter. This connection of observed pair production with established theoretical frameworks expands the scope and relevance of the original discovery to broad physical principles. Section 11. Development of new particle accelerators technology enabled by discovery. The discovery of the positron spurred the development of new particle accelerators designed to create and study antimatter in controlled laboratory settings. Scientists recognized the potential of using accelerators to produce beams of positrons, allowing for detailed investigation of their properties and interactions. This development led to the construction of increasingly powerful accelerators, pushing the boundaries of particle physics research. The technological advancements, directly motivated by the discovery, illustrate the profound influence Anderson's work exerted on subsequent scientific endeavors. The creation of these accelerators shows a direct consequence of scientific curiosity and its translation into practical tools. Section 12. The role of the positron in quantum electrodynamics. The positron played a central role in the development of quantum electrodynamics, the theory describing the interaction of light and matter. QED provided a more complete and accurate description of the positron's behavior, incorporating quantum mechanical principles and relativistic effects. The theory demonstrates how the positron is not simply a hole in the sea of electrons, but rather a distinct particle with its own properties and interactions. Quantum electrodynamics provides a more nuanced theoretical framework, enhancing the understanding of the positron beyond its initial identification. The integration of discoveries into more comprehensive models highlights the iterative process of scientific discovery and refinement. Section 13. Positron emission tomography application of discovery. Beyond fundamental physics, the discovery of the positron had significant implications for medical imaging. Positron emission tomography, known as PET scanning, utilizes radioactive isotopes that emit positrons. These positrons annihilate with electrons in the body, producing gamma rays that are detected by the scanner. PET scans provide detailed images of metabolic activity within the body, allowing for the early detection of diseases such as cancer. The translation of a fundamental physics discovery into a powerful diagnostic tool underscores the potential for basic research to have profound practical applications. The medical technology demonstrates the long-term societal impacts of Anderson's work. Section 14. Subsequent refinements and adjustments to mass measurement. While Anderson's initial estimates of the positron's mass were remarkably accurate, subsequent experiments employing more sophisticated techniques refined these measurements. Precise measurements of positron mass confirmed that it is indeed identical to the electron's mass, further validating the positron's status as the electron's antiparticle. These refinements, though not significantly altering Anderson's initial conclusions, improved the precision of fundamental constants and our understanding of the symmetry between matter and antimatter. These small adjustments to initial measurements represent the iterative nature of scientific investigation and the continuous pursuit of more accurate data. Section 15. Early reactions and skepticism within the scientific community. Despite the rapid validation by many physicists, some initially greeted Anderson's discovery with skepticism. This skepticism stemmed partly from the radical nature of the discovery itself, challenging established notions of particle composition. In addition, some researchers questioned the accuracy of Anderson's measurements, suggesting that alternative explanations might account for the observed particle tracks. However, the overwhelming evidence supporting the existence of the positron eventually silenced these dissenting voices. The initial skepticism highlights the inherent resistance to paradigm shifts within the scientific community, but also the crucial role of rigorous testing and validation in overcoming such resistance. Section 16. The Nobel Prize and recognition of Anderson's achievement. In recognition of his groundbreaking discovery, Carl Anderson was awarded the Nobel Prize in Physics in 1936. The Nobel Prize represents the ultimate validation of a scientist's work, acknowledging its profound impact on human knowledge. The award to Anderson solidified the positron's place in the pantheon of fundamental particles and cemented Anderson's legacy as a pioneer in particle physics. The award recognizes the importance of Anderson's contribution to science and reinforces the value of fundamental research. Section 17. The concept of antimatter and its implications for cosmology. The discovery of the positron opened up a new frontier in physics, leading to the exploration of antimatter. Physicists theorized that for every particle in the universe, there exists a corresponding antiparticle with opposite charge and other quantum properties. This prompted the question of whether entire antimatter galaxies or even an antimatter universe could exist. While no larger-scale antimatter structures have been observed, the concept of antimatter remains a central topic in cosmology, particularly in the context of the Big Bang theory. The subsequent investigations into antimatter broadened the scope of inquiry prompted by the initial discovery. The search for larger-scale antimatter structure in the universe represents a challenge to existing cosmological models. Section 18. Anderson's continued research on muons. Another discovery. Following his discovery of the positron, Anderson continued to make significant contributions to particle physics. In 1936, he, along with his student Seth Neddermeyer, discovered the muon, another fundamental particle initially mistaken for a heavy electron. This discovery further expanded the understanding of the particle zoo and deepened the mystery of fundamental constituents of matter. The subsequent discovery of the muon highlights Anderson's continued contributions to particle physics beyond the positron. The discovery reinforces the idea that scientific innovation often leads to further discoveries and challenges. Section 19. The lasting legacy of Anderson's work. Anderson's discovery of the positron stands as a landmark achievement in the history of physics. His meticulous experimental work, combined with insightful analysis, revolutionized the understanding of fundamental particles and paved the way for new fields of research. The positron's discovery not only validated Dirac's theoretical predictions but also opened up new avenues for technological innovation, particularly in medical imaging. The enduring legacy of Anderson's work spans from fundamental science to practical applications. Section 20. Anderson's approach and experimental rigor. Methodological considerations. Anderson's approach to experimental physics is characterized by its meticulousness and rigorous attention to detail. He carefully designed his cloud chamber experiments to minimize uncertainties and to allow for unambiguous identification of particle tracks. He scrutinized his data carefully, considering alternative explanations and potential sources of error. This commitment to experimental rigor served as a model for subsequent generations of physicists. The emphasis on experimental rigor highlights a critical aspect of successful scientific inquiry. The commitment to meticulous data analysis and critical assessment is crucial for reliable results. Section 21. The evolution of cloud chamber technology. It's important to note that cloud chamber technology, while revolutionary for its time, was eventually superseded by more advanced particle detectors, such as bubble chambers and electronic detectors. These new detectors offered improved resolution, higher data acquisition rates, and greater flexibility in experimental design. However, the cloud chamber remains a valuable tool for visualizing particle tracks and for introducing students to the principles of particle detection. Although superseded by newer technology, The cloud chamber's historical significance remains substantial. Offering a tangible illustration of particle behavior, the cloud chamber stands as a testament of human ingenuity and its impact on scientific progress. Section 22. The ongoing search for dark matter and antimatter. The discovery of the positron and the subsequent exploration of antimatter have inspired ongoing research into the nature of dark matter and dark energy, the mysterious substances that make up the vast majority of the universe. Some theories propose that dark matter may be composed of particles that are their own antiparticles, while others suggest that dark energy may be related to the vacuum energy of the universe. The search for dark matter and antimatter represents a continuation of the inquiry that began with the discovery of the positron. These investigations reflect the persistent efforts of scientists to understand the fundamental constituents and properties of the universe. Section 23. The future of positron physics. Positron physics remains an active area of research, with ongoing efforts to develop new techniques for producing and manipulating positrons. These efforts include the development of positron traps, which can confine positrons for extended periods, and the creation of antihydrogen atoms consisting of a positron orbiting an antiproton. These experiments have the potential to shed new light on the fundamental laws of physics and to test symmetry between matter and antimatter. The continued exploration of positron physics promises to yield further insights into the nature of antimatter and its role in the universe. Ongoing experimental efforts showcase the ongoing efforts to leverage the discovery and explore its implications. In conclusion, Carl Anderson's discovery of the positron in 1932 represents a watershed moment in the history of particle physics. His meticulous experimental work and insightful analysis not only confirmed Dirac's theoretical predictions, but also opened up new avenues for scientific inquiry and technological innovation. The positron's discovery not only validated Dirac's theoretical predictions, but also opened up new avenues for technological innovation, particularly in medical imaging and materials science. As we continue to explore the mysteries of the universe, the legacy of Anderson's discovery will undoubtedly continue to inspire and guide us. His work serves as a powerful reminder of the transformative potential of scientific discovery and the enduring quest to understand the fundamental constituents and forces that govern our universe. The impact of Anderson's work resonates through the scientific community, continuing to propel forward the understanding of the nature of reality.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.